Indiana weather data file. That should be under the in-class data folder on Canvas. So it's not blank. It has kind of all this work in here. I'm going to, actually, this is not the one that you would see. Let me see. I had, oh, there's one I didn't save. Let's see if it's this one. I think it is. Yep. Sorry, it should look something like this if you go to that temp-normal sheet. Right? So we have a bunch of worksheets down here. Some of it was like, I think I created the time series graph somewhere on this one. Maybe it was here. Here it is. Yeah, right. Then I've got rain. But we're going to use this temperature one. Right? So not only does rainfall follow a normal distribution, temperature is pretty close to a normal distribution as well. So what I have here is every single month in Indiana for every year, whatever the average temperature was that month. Right? And I think this is a little different in the slides because I think I have, yeah, I've got some newer data here. Okay. So I go up here, and if I wanted to find the overall, right, kind of start labeling this. I'll get out of here. Let's go to view, zoom, so we can see this a little better. Right. So this first row, I calculated the mean, the variance, and the standard deviation. Right? Won't really review that. It's pretty easy, right? All I did was use my average function to find the average temperature in every year, the variance, and I kind of did this a little tricky way. You didn't have to use the annual. You could just select all these. Don't worry too much about that. And then to get the standard deviation, I would just take the square root. But if I wanted to break this down by month, notice I could take the average of the column that has June temperature. That would give me my mean June temperature. Take the variance of that June temperature column. It gives me the variance on June temperature. And then just take the square root of the variance to give me my standard deviation. If I wanted to, I could use that built-in standard deviation function as well. It should give me the same value. Okay. So I did this for 3 different months, right? June, July, and September, right? And I'm actually going to use this value for all of them here, just to give us an idea about what's happening. Okay. So I'm going to delete this real quick and kind of rebuild it for you. So we're going to kind of start off with the same cutoff value. So the first thing that we're going to try to do is find the probability that this June we see an average temperature of 71.4 or lower. Okay. So we know that if we're doing this by hand, we would turn this into a z-score, then look that z-score up in the table, right? And because we wanted the area to the left, that's what the table told us, we'd be done. Right? So we're going to use Excel just to do some math for us first. Okay. It's not going to be a built-in function. We're just going to do math. How do we calculate the z-score? Well, I'm going to take the x value I'm interested in finding the probability of being less than, right, 71.4. Subtract the mean for June temperature, and then divide by the standard deviation of June temperature. Now, if I do this, why is this going to be a problem? I just got a z-score of 43. That doesn't seem quite right, right? I'm looking at a value that's not very far from the mean. So what did I do wrong here? Yeah, right. So a lot of the stuff that we're going to be doing moving forward, we're going to do some of our math in Excel, like, not a built-in function, but just typing in a formula. We have to be really, Excel doesn't recognize order of operations errors because it doesn't know exactly what you want it to do. So we have to be really careful about how we're entering in equations when we're doing math in Excel to make sure that we know that order of operations is working correctly, right? Often that's just throwing in some parentheses, okay? So now we're going to find the difference between our cutoff value and the mean, and then we're going to take that difference and divide it by the standard deviation. So that's what we wanted to do. So we end up with a z-score of 0.21, right? So it's only about 0.2 standard deviations away from the mean, okay? Now, if I copy this across, it's going to update everything. So I'll be using the next cutoff value for that month, but it's going to update my mean and my standard deviation to then be looking at July. So if I drag this across here, we start getting different z-scores. And this kind of makes sense, right? If we look at these 3 months, July has the highest, and I think I did September here. Did I do September? This is not September. I have this labeled wrong. This is August. I forgot a month there. So if I look at the average temperature in July, it's the highest in Indiana. So I know that seeing 71.4 in July, well, that's something below the mean, right? In fact, it's quite about 1.5 standard deviations below the mean. So it's going to be less likely I see the average temperature be 71.4 or lower in July than it would be in June, right? And that's because June has a much lower average, right? 71.4 in June would actually be something that's above the average temperature, right? But I can find the probability in each one of these months that I see that average temperature of 71.4. So how can I do that? Well, I've got my z-score. I now use this built-in function called norm.s.dist, right? So what this function does is essentially what we were doing with the table. That's what this function does. It looks up a z-score, and it basically looks up in the table for you, and then tells you what probability you would have found. Now, what it's actually doing, remember those tables, all those probabilities come from integrating that function from -infinity up to whatever that z-score is. So really what Excel is doing is it's doing that integration behind the scenes. But if it's easier to think about, it's basically just looking up that z-score in the table for you. Okay? So I tell it the z-score that I want it to look up. And then we're always going to say comma 1 here. So this is cumulative, right? The tables were always giving us cumulative probabilities. So we're always going to put a 1 in there. If you put a 0 in, I don't know. It does some goofy thing in Excel where like, if I didn't make this cumulative, what should the probability of any one value actually be? 0. So what it does is it's not really not making it cumulative. It's looking over like a certain interval based off of the kind of, looking at like an infinitesimally small interval. So, but we're never going to use it. It doesn't really have any practical use for us. So we're always going to put comma 1 here, which means that this function works just like you would looking up the z value in the table. Okay? So sure enough, 0.21, if I were to look that value up myself in the table, so I go down here, if I had a z-score of 0.21, 0.5832, 0.5849. Well, notice this can get a little more exact because it's not constrained to 2 decimals. It didn't have to round the z-score and look up 0.21. It could actually use this value and then integrate the function. So in Excel, we can be a little bit more exact. All right, so it's kind of helpful. Any questions kind of up to this point? All right, so we're just using that, norm.s tells Excel use a standard normal distribution. Then you just tell it your z-score, and then comma 1 to give you the area to the left of that z-score. Okay. And I could copy this over, right? You can kind of think about the probability that the average temperature in July is 71.4 becomes less likely because, right, now the average temperature in July is a little bit higher, so seeing 71.4 isn't near as likely. And then as the temperature kind of falls back down, the average temperature in August is a little bit lower. Well, now seeing the average temperature of 71.4 lower becomes a little bit more likely. So it's kind of this probabilities, or how we would find those probabilities for the standard normal distribution in Excel. Okay. Any questions on that? So what if I wanted to find the probability of being above a certain z-score? How could I use that norm.s.dist but find the probability of being above a certain z-score? Simply, right? This is where if I've got the area to the left, if I want to be greater than something, I want the area to the right, it would just be 1 minus that. Right? So that would copy that over. Now I've got kind of the probability of seeing an average temperature above that cutoff point for each month. Any questions on that? It shouldn't be too bad. So we have another function that makes life even easier, right? So we've got this norm.dist function. So sometimes we might want to see what that z-score is, right? We might just be interested in how many standard deviations away from the mean that we are. Sometimes we don't care. Ultimately, what we want is just the probability, right? So the norm.dist, what it will do is you tell it the cutoff value you're interested in, x, comma, what is the mean of the variable that you're looking at? So that's up here, comma, the standard deviation of June temperature. And then just like norm.s.dist, comma 1 is the last thing, tells it to make it cumulative. So what this function does is it basically calculates the z-score for you behind the scenes. it has the 3 components it needs to calculate the z-score. So it does that for you behind the scenes, then looks it up in that standard normal table and returns to you the probability of seeing that z-score or anything below it. Now, remember, when we're saying things like, what's the probability I see this z-score or anything below it? What we're really saying is, what's the likelihood that I saw a value that was this many standard deviations away from the mean or anything even further from the mean? So even though we're looking up the z-score, it really relates back to whatever that original value we were interested in was. So here, we don't even have to worry about even thinking about the z-score because we're just going to put in the value and say, okay, I know that Excel's going to turn this into a z-score and tell me the probability of seeing something that many standard deviations away from the mean or even further. But ultimately, really how I want to translate that, it's the probability of seeing 0.47 inches of rainfall or anything less, or a temperature of 71.4 or anything less than that, right? So we have to use these z-scores as kind of an intermediate step, but ultimately these probabilities speak to whatever that original variable x was. So here, it's going to be the probability that in June, we see average temperature be 71.4 or less, right? So we hit enter here, sure enough, we get the exact same thing that we found before. And I could copy this over, and I'm getting the exact same probabilities as I did before. I just have a little bit less work. I don't have to calculate the z-score. Excel does it behind the scenes for me. The only issue with this is if I ever want the z-score, well, you know, this function kind of keeps it, doesn't like store it anywhere where I can look at it. Okay. Any questions over anything there? So the first part of that Excel assignment that I'll get up there will kind of look similar to that, where you'll just be given a variable. The thing I want to do today in class is take a little bit of a look into Excel. So I'm going to sit down so I can type easier. All right, so we kind of worked with some of this, and you can ignore this for right now, but we worked through some of these norm.s.dist and norm.dist examples last week. I'll kind of work through and show you how we could do the inverse work in Excel as well. So I'm going to go to this inverse transformation worksheet that I have in that Indiana weather data file. And I have the exact example that we just worked through in class with that exam score. So I kind of set this up in a nice way. So for right now, I'm going to delete these 3 values, just to kind of show you how we use these functions. So I've got my mean up here, my variance, and here's that area that I wanted in the left tail, right? So this was like when I wanted to find the bottom 40% cutoff. Or I could do, what was that cutoff for the 90th percentile, right? Or what was the test score that was 90% of test scores below it? And that was the first example we worked through. So if I want the probability that x is less than or equal to some cutoff value, and I know that that probability I want is 0.9. So I'm trying to work in reverse. I know the probability, trying to find the x value, right, or the test score that is the cutoff for the 90th percent. So I'll do norm.s, norm.inv. Okay. So if I use this norm.inv function, I then tell Excel, okay, what probability or what cumulative probability do you want the area in that on the left side there? Well, I wanted it to be 0.9, right? That was kind of the example we worked through. Comma, what's the mean? Have the mean up here. And then comma, what's the standard deviation? Well, I've got the variance in a cell here. I could calculate the standard deviation in a different cell if I wanted to and then reference that. Or I could just say, well, I know that the standard deviation is always going to be the square root of the variance. So notice I can use like multiple functions and things in Excel all within the same cell. I don't have to break it down to parts. Now I can, and for you guys as you're learning it, that is often maybe a little more helpful to kind of keep track of your work and identify maybe where you're going wrong or where you have an error. But once you start to get familiar with them, you can put everything in the same cell. So what this will do is it'll take the area that you told it, right, 0.9, go to the table, look up 0.9, find the corresponding z-score, just like we did by hand, then use that z-score, the mean, and the standard deviation, plug it into the inverse transformation formula, and spit back out at you what that cutoff value would be to see 0.9 in that left tail. Sure enough, we get, I think ours, we had to do some rounding. So we had like what, 82.26, I think. Well, here we can get very exact, right? We don't have to do any rounding of our z-scores to the second decimal, or the probability we find is going to be a little bit off of 0.9. We can look up exactly 0.9. Okay. So Excel allows us to be a little bit more precise than doing it by hand using those tables. Now, if you were doing it by hand, you can still be precise if you want to do the integration, but that's, most people don't like to do that every single time they want to find the probability from a normal distribution. Okay. Any questions on that? Okay. So the other way you could do it, right? If we remember, our inverse transformation formula was something like this, right? Take the mean, add the z-score times the standard deviation. So instead of using the norm.inv, just like we had norm.s.dist and norm.dist, we can find first the z-score that would be the cutoff for that probability of 0.9, or that cumulative probability of 0.9, or the area to the left of 0.9, right? All different ways of saying the same thing. Okay? So I can use the norm.s.inv, which says, okay, use a standard normal distribution and just return to me the z-value, or the number of standard deviations away from the mean I need to be to get that probability of 0.9 below that z-value. So I tell it the area that I want to the left from that 0.9. This will give me the z-value. Remember, when we looked it up, we were between 1.28 and 1.29. So we had to use the higher of the two. That's why we got, our answer might be a little bit different than what Excel tells us, because Excel knows it's in between 1.28 and 1.29, but it can find the exact value that it is, right? So 1.28155, okay? So now that we have that z-value, we can use Excel to do a little bit, just basically do the math for us, just like a calculator, right? So I'll take my mean, I'll add that z-value, and I'll multiply that z-value by my standard deviation, which once again, I'm going to do the square root of the variance there. Okay. So two different ways of doing the same thing. Hopefully when I hit enter here, I get the exact same cutoff value, right? Because it still should be the cutoff value for the 90th percentile, right? Sure enough, get the exact same thing. Okay. So we can always do the intermediate step, right? Like use the norm.s.inv and then plug it into the formula. Just like when we did norm.s.dist, found the probability that we wanted, right? We had to first calculate the z-score to put it into norm.s.dist, or we could just skip it all together, skip the intermediate steps, use norm.dist, or here, skip all the intermediate steps, just use norm.inv. Any questions on anything that we did there? Want to see something again? And if I have it set up this way, it's kind of nice, because now what if I want to find the bottom 40%? That was the second problem. Well, I've got everything referenced, just updates everything automatically, right? I could find the cutoff score for 50%. What should that? I'll eventually post the complete version of this once we work through it in class. But for now, it is blank. So let me zoom in so we can see this here. So I've got a couple kind of things going on here. One of them I'm going to change later, but for now, we'll kind of look at this data set. We've got a bunch of different universities. They're male, female, and total undergraduate enrollment. So if you can kind of see the titles, I kind of minimize them just so that we don't take us up as much space. So what I'm going to do is try to build a confidence interval based off this sample for what the true population mean enrollment size is for universities. So I don't have every university here. I've got like 100 of them. So we're going to build a confidence interval based off this sample. Now, this is where it gets a little goofy, because I said we have to walk before we can run. So we have to understand how we work with a population variance before we only have a sample variance. So here, assume that someone told you, you don't have the population data, but someone told you the population variance is whatever I have in this cell, right? 68, is that 68 million, right? So I have a known population variance, right? And actually, I'll just label this just so we make sure we know that this is like something we were given, this population variance. Ignore the cutoff for right now. That's something else that if we have time today, I'll kind of show you. We've really already looked at examples of what I was going to use this for. We use a different data set when we were looking at how we do, what's the probability we're above or below a certain cutoff. We did that with like the Indiana weather data. So we can kind of ignore that for now. So I'll actually just to kind of move this down here and move my sample size up here because we don't need this for right now. So if I'm looking at that total undergraduate enrollment, I can find my sample mean by simply finding the mean in Excel, which is the average function, right? So equals average. I'll select that very first observation, hold Control Shift or Command Shift on a Mac, hit the down arrow. It selects all of my observations for me. I then hit Enter, sends me back up, and I've got my sample mean here, right? So once again, if it kind of helps to label these a little bit more specific, that's my sample mean that I'm calculating. So I only have sample data here. I don't have every university. To get my sample size, we said we can count the number of observations we have by using the count function, right? So I'll select that variable in my count function, hit enter, got 111 universities here, okay? So it's a pretty good, pretty high sample size. Now down here, I'm going to start to show you how do we create our confidence intervals based off this sample mean. A lot of it's just going to have Excel do some math for us. Now, I think it's probably easier to set it up in this first way I'm going to show you. So down here, one of the components that we needed in this confidence interval equation was the standard deviation of my sample means. If I wanted to, I could enter all this into one cell in Excel if I wanted, but I'm going to break it down just I think it makes it a little bit more clear. So down here, I'm going to find the standard deviation of my sample means. Oh, I did not want to do that. Hold on. There we go. So equal sign, I need to take the square root of my population variance divided by my sample size. So I come up here, take my population variance that was given to me, and I'm going to then divide that by my sample size. Okay. So that should give me this standard deviation of my sample means here. Okay. The next thing that I need, I've got that part done, I need my sample mean. Well, I have that up already in a cell. The only other thing I need is that z-score that gives me the desired alpha over 2 in each side of my confidence interval. Okay. So we already actually have looked at the function that we can use to find that z-score. In practice, we went to the table, found the value in the middle, right, that probability that was as close to alpha over 2 as we could, and then went over and up to the row and column heading and found that corresponding z-score. In Excel, that process, right, we're looking up the probability to then find the z-score that corresponds to that. We're working in reverse, or we're looking at the inverse kind of transformation. So we said we can use the norm.s.inv function in Excel to do that for us, right? We don't have to physically use the table. Excel will like kind of look it up in the table for us. So what do I have to tell this function? Well, I just have to tell it the area I want in that lower left tail. Okay. So I want alpha divided by 2. All right. Now the problem is going to be if I look up, let me erase this so we have a visual here. Where's my eraser at? So if I have I want to look at the z-score that gives me alpha over 2 in that lower left tail, and then the positive one would give me alpha over 2 in the upper right tail. So I can tell that function alpha over 2, but it's always going to tell me that negative z-score, right, or the negative z value. But remember, that's already built in when we calculate the upper and lower bound. Okay? So I kind of want to ignore that negative sign, right? So if I hit enter here, it gives me negative 1.644. If we did this by hand, we would have found that we were in between negative 1.64 and negative 1.65. Here we can be a little more precise with Excel. Yeah. Yeah, so the purpose of the Excel assignments, right, is you should be using all the built-in functions and formulas in Excel to do that assignment, right? So if you just type in 1.6, well, good on you if you do the integration and find it out to like the 4th or 5th decimal point. But if you just put in 1.64 here or 1.65, you're not going to get full credit for that, right? Because the purpose of these Excel assignments is to be using the built-in functions and formulas in Excel, okay? So these is like problems, what, 2 and 3, I believe, are the ones we haven't covered on that Excel assignment. So we'll go over both of those today. And then we had that due date changed on that. I can show that to you here right now. All right, so that's the end of the week, all right? End of the day on Friday, okay? Gives you time to kind of work through this. If you have any questions, come to office hours or email me, all right? But we'll work through kind of those today. Any other questions before I keep moving here? So it's negative. I don't want it to be. I just want the z value, or I just want the absolute value, right? So if I use this absolute value formula in Excel, ABS, it just, oh, come on. It just drops that negative sign, right? So now I should get the same value, but notice positive. Okay. Now, I'm going to build 3 confidence levels here. I'm going to insert a column. So I just right-clicked and inserted a column here. Because I just want to have, be able to connect this. At the alpha of 0.1, what level of confidence does that correspond to? 90, and then 95, and then 99. Right? So I'm going to build 3 different confidence levels, and I can do it relatively quickly. Right? The only thing that's changing when I'm building a confidence interval for a different confidence level, right, different level of confidence, is that z value that I need. Okay? So if I copy this down, it's going to update to my new alpha, so I can get the z values I need for those 3 different levels of confidence pretty quickly. There's no need to type it in again, right? If I've constructed it this way. So the next thing I'm going to do, I have all the components now that I need to find my upper and lower bound. Okay? So for my lower bound, at this point, it's really just using Excel to be your calculator, right? So the main advantage in Excel here when I'm doing confidence intervals is to use that norm.s.ind function. Okay? Now, if you try to do this and you Google how to do confidence intervals in Excel, there are some other functions that we're not going to cover. The reason I don't cover them is because they are somewhat limited in their use once we get to future topics. So you can try to use them. Occasionally people will do it. And if you use it correctly, I'll give you full credit. But I would say 95% of people that try to use the other form that you might find if you Google this, don't do it correctly and don't get points because they get answers that are wildly incorrect. Right? I'm showing you this way. It's probably the most universal to all of the types of problems we'll kind of see here for the next couple of weeks. So try to set it up the way that I'm showing you it this way for a reason. This is the easiest way to do it. And this is the way that it'll probably kind of fail safe to not make as many mistakes. Okay? But at this point, it's really just using Excel to be my calculator because all I'm going to do is take my sample mean. I'm then going to subtract my margin of error to get my lower bound. So I'm going to subtract that z value, or the number of standard deviations the way I want to go, and then multiply that by the standard deviation of my sample means. It's as easy as that. I'm just using Excel to be my calculator here. Clicking on the values. Notice I don't have to round to 2 decimals. Right? So I hit enter. I've got my lower bound for the 90% confidence level. If I wanted my upper bound, instead of typing this in again, I think probably an easier shortcut to save a little bit of time. I think I've showed you this before, but if I double click on the cell so it shows me the formula, I can copy that. I'll hit enter to get out of the cell, double click where I want the upper bound, and paste it. When I copy paste this way and I don't just drag across cells to copy, none of the cell references change. I should get exactly the same value. Okay? But the upper bound, it's going to be the exact same equation, except instead of subtracting that margin of error, I'm going to add it. So now I've got my upper and my lower bound. So with 90% confidence, I can say the true population mean enrollment in D1 universities is somewhere between 19,100 and 16,500, or whatever the exact numbers are. Now, if I try to copy these down, I'm going to run into a problem. Well, that definitely does not look right? So the issue is, all my cell references started to change. And when I'm doing different levels of confidence, the only thing that's really changing is that Z value that I'm using, okay? So I'll go back up here. I'll say, oh yeah, the only thing I want to update when I copy this down is that Z value. So I'm going to freeze everything else. So F4 or Command T on a Mac, I'll freeze those. I have to do the same for my upper bound. The only thing I want to change is that Z value. So freeze everything that isn't a cell reference for that Z value. Okay. Now when I copy these down, it keeps that standard deviation of my sample mean the same, and it keeps the sample mean the same. The only thing that's updated is that Z value that I was selecting. Okay. So I've now got 3 confidence levels relatively quickly. I think a lot quicker than I could do by looking up, trying to find these Z values by hand. And also I can be a lot more precise. I don't have to round anything to the second decimal here. Okay. Any questions over anything that I did here? Want to see a cell again, or? Okay, so point out a couple things. I said earlier, when we want to look at a larger alpha value, right? So if we're going from like 0.01 up to 0.1, that should mean I have a larger area in my tail. My Z value should be getting smaller or closer to 0. Sure enough, as I'm going to larger alphas, my Z values are getting smaller. We also said that if I'm going from smaller to a larger alpha, the fact that Z value is smaller, my margin of error is smaller, and my confidence interval gets more narrow. So my lower and upper bound should be getting closer to each other, right? So notice my lower bound is getting higher, my upper bound is getting lower, or those two things are getting, I'm getting a much narrower kind of range of values. Okay. Another thing that we could have done, instead of using this absolute value function, oops, there we go. Notice I know that I want alpha over 2 in this tail, in the lower left tail and the upper right tail. Well, if I want alpha over 2 right here, the area to the left of that would be what? Just 1 minus alpha over 2. If I just want the total area to the left, right, I know I want 1 minus alpha over 2. So if I tell that norm.s.i function 1 minus alpha over 2, it should give me that Z value, but positive, and I shouldn't have to use the absolute value function. So let's try that out, see if I'm just full of it. All right, so 1 minus alpha over 2. Sure enough, it should, if I copy this down, give me the exact same values as if I use the absolute value kind of way of doing this, right? And just telling that norm.s.inv, just telling it alpha over 2. And so kind of 2 different ways of finding that Z-score to just get the value to be positive, okay? Any questions on that? Okay with that? All right, so there was one more thing I wanted to show you here, and now I don't remember what it was. Oh, I know what it was. So since we already talked about things that change the size of the interval, let's assume for a second that, and this is hypothetical, but let's assume I found the exact same sample mean, but instead of from this sample of 111 schools, let's say I had another sample of 300 schools. Okay. So if I had found the same sample mean, but it was from a sample of 300, what's that going to do to my intervals, right? Well, my sample size is larger. It's going to drive down that standard deviation of my sample mean. So when I hit enter here, everything will, right? I had cell references, so everything will update. So my standard deviation of my sample mean should get smaller from a larger sample size. My margin of error would then get smaller, and I should get narrower intervals. So changing this from the actual sample to a hypothetical sample of 300, this should get smaller, and my intervals should also get smaller. Sure enough, went from what, 700 to the 400 something, and these are kind of much narrower intervals, right? What were they before? So instead of 17 to 1860 or 18600, they were 16,000 to 19,000, right? So changing that sample size to 300 narrowed my confidence intervals because it was decreasing that standard deviation of my sample means. Okay. Any questions over that? Now, that was kind of purely a hypothetical kind of practice, right? Our sample size is what it is. But that kind of shows you that having a larger sample is always more beneficial when we're trying to build these confidence intervals. Okay. So if there's no more questions on that, we're going to tell. We can also do sample proportions. Right? So over here, right, I'm going to do a similar setup. I'm going to calculate the intermediate value as well, just to prevent myself from making some order of operations or parentheses mistakes. So here I'm going to find the same standard deviation of my sample proportions, right? It was kind of represented by this. I can find my sample proportion or my mean proportion here. I think I'll call it sample just to kind of line up with the way that I usually say it. Now, to find a proportion from data, I had this example originally, which was I wanted to say what proportion of schools have more than 10,000 students. I've got a, I think, more interesting example that we're going to actually do. So I'm going to delete this column. If you want to follow along, just type in exactly what I have. So here I'm going to do, does the school have more female undergraduates than male? Okay. So I just deleted that column of data, highlighted it, hit delete. I'm then going to use this if statement. Now, I wouldn't expect you to do this on like a homework or anything, but it's a way that you can construct kind of one of these 1-0 variables kind of easily. Now I'm just going to say, okay, if female undergraduate enrollment is greater than male undergraduate enrollment, that's what I want to check to see if that's true. If it's true, comma, put a 1. If it's false, comma, put a 0. Okay? So I can enter this in for the very first observation. And then if I get this to be this bolded black plus sign and I double left click, it'll fill this in for every observation I have here in my data set, right? So every time I see a 1, that means female undergraduate was greater than male undergraduate enrollment at that university. Every time there's a 0, it means they had more male undergraduates than female, okay? So you can kind of notice Ball State's pretty skewed towards female, at least in 2012 it was. Okay? So I've got all these 1s and 0s. If I simply take the average or calculate the mean for a binary variable, what that's really doing is it's adding up every single observation. So it's adding up 1 plus 1 plus 1 plus 1 plus 1 plus 0 plus 1 plus 0. Well, every time there's a 0, it doesn't influence my numerator at all. And then once it adds all those up, it divides by the sample size. I think I erased it already, but that's really counting up the number of schools that have more females than males, and then dividing it by the total number of schools in the data set. That's just my sample proportion. So in practice, when I have a 1-0 variable in my data set, if I find the mean of it, really what I'm doing is just finding my sample proportion. Okay. So anytime I have a 1-0 variable, finding the mean of it, I'm really just calculating a sample proportion. And then sample size, we can still use that count function. Go over here, select that variable. Now I've got everything I need. I've got my sample proportion, I've got my sample size. The only other thing I need to do is look for that z value that gives me alpha over 2 on either side of my interval. Okay. Well, that's going to look no different than what we were doing over here, right? So norm.s.inv, I want alpha over 2 on each side of my interval. I have to remember, oh yeah, this is going to give me the negative value. So I need to take the absolute value. Oops, that's not what I want to do. There we go. Put my other parenthesis. Should get the exact same value as before because I'm looking up the same alpha over 2, right? I'm using those same kind of benchmark values. Copy that down. Now I get my z values. From here, I can calculate that intermediate step, which is the standard deviation of my sample proportions. That's just going to be the square root of my sample proportion. I'll move this out of the way so you can see it. Times 1 minus my sample proportion divided by my sample size. Once I have this, I've got the 3 components that I need to find my upper and lower bound. So, so equals, take my sample proportion, subtract that z value times the standard deviation of my sample proportions to get my lower bound. If I want to copy this down, I said, oh yeah, I've got to freeze everything except for my z value. All right? When I'm building different levels of confidence intervals, the only thing that changes is my alpha, or that is z value. Okay? So once I have this, I could copy that down to get my lower bound. Now I could retype that same thing in for my upper bound, or I could use that, what I think is a shortcut, which is double click on the cell to see the formula, copy it, hit enter to get out of the cell, paste it over here. And now the only thing that we have to change for the upper bound is we're adding that margin of error instead of subtracting it. Okay. Now I copy this down and I've got my three confidence level or intervals built relatively quickly. Okay? So real similar process to what we're doing with the sample mean. It's just that, right, the equation that we had changed a little bit because that standard deviation of our sample proportions was a little bit different than that standard deviation of our sample means. Okay. So I went through that kind of quick. Do you want to see any of those cells again, or kind of a question or anything there? So mainly what this exploits is the use of that norm.s.inv function to kind of look those values up in the table for us. Other than that, I mean, one new thing that we're kind of looking at is if we just use the mean or the average function for a 1-0 variable, that gives us our sample proportion. And then from there, it's kind of just using Excel to be a calculator, right? So we don't have to round things. We can be very exact, right? And we can get this out to whatever decimal level we want. So this should be everything you need to kind of do those last two problems in the Excel homework. The first problem comes from like the old stuff where we're even looking at samples. We're just looking at an original normally distributed variable. Okay. Questions on this? Now's the time to ask. Okay with this? So I've got one other thing I'm going to show you. I put another file up there called CI grade data. Okay. So, you know, maybe you don't believe necessarily what I'm saying, that, you know, the whole idea of these confidence intervals is that when I take one sample, that I can be guaranteed that 95, so if I want to do 95% confidence level, 95% of the time, if I just take one sample and build a confidence interval around it, it will include the true population mean. Now, what I'm going to do here is kind of cheap, okay? So I've got population data here. And this was like every student, I think, that has taken, well, it's pretty up to date. Almost every student has taken a stats class from me. And what their grade was to the nearest integer, right? Just to make the numbers a little bit easier to look at. So I can calculate the true population mean. I can calculate the true population variance, and I have my population size, right? What I then did was kind of use this thing in Excel, which is a random number generator. So I'm generating a random number from 2 all the way down to whatever the, what is it? E2 or, oh yeah, right here, to the very last kind of person in my data set, right? So I'm going to generate these random numbers so that I'm randomly selecting a student ID here. And the idea was just kind of assigning them 1 through 431 or whatever. So I'm going to have a bunch of different samples. So here I kind of had the first 3 labeled. We can kind of see out here. Here's all my other samples as well, right? So I generated all these random numbers. Oh, here, I'll show you these ones, right? For 1,000 different samples. So I've got 1,000 samples. They're all of size 50. So notice I generated 50 random numbers for 1,000 different samples. For each one of those samples, I then calculated my sample mean, right? So I've got 1,000 different sample means. I'm then going to construct confidence intervals around those sample means. I think what I chose here was, we'll start out, we'll do a 99% confidence level, okay? So I set alpha to be 0.01. So down here, I had an equation. Now, I didn't break it down into parts, right? Notice I kind of even found the z values all in the same cell. So when I broke it down before in those examples, I could do it all in one cell. If I don't want to see what those z values are or the standard deviation of my sample means, I can type this all in at one time, right? Now, I can kind of have an example here where I knew the true population variance because I had the population data. So even though I'm basing this confidence interval off this first sample, I can use that true population variance because I also have the population data. So I build my lower bound, and same thing, but I add to get my upper bound. I then kind of did something I wouldn't expect you guys to do, but I played around with some if statements. So basically what I'm doing here is I want to put a 1 if the true population mean that I have up here is above the lower bound or below the upper bound. Said differently, I'm just putting a 1 there if it's in my confidence interval, and let's see if there's any zeros here that are nearby. Maybe these all, come on. Let me see if I can get, so every time I click on these, it'll generate new random numbers. Well, I'll change alpha so I can show you. We'll change alpha to 0.1, right? Should get a lot more. There we go, right? So notice for this confidence interval, population mean just fell outside of it. For all these other ones, that population mean was somewhere within that range. Okay? Well, then what I did is said, okay, I'm just going to add up the number of times my population mean was in my confidence interval across those 1,000 different samples. So I added all those ones up, and then I have the number of samples here, which is 1,000. So then to find the percent of my confidence intervals that included the true population mean, I just took the number that included it, divided by the total number of samples, 1,000. And notice when I set alpha to be 0.1, for these 1,000 different confidence intervals, 90.7 of them included the true mean, which lines up with, that's why I'm saying it with 90% confidence. Now, it's not exactly 90 because I only took 1,000 samples, right? To get it to be even more precise, I should probably have like 10,000, or theoretically, I really need an infinite, which isn't practical, right? But I'm just trying to use data to kind of prove this to myself as opposed to just the mathematical proof. And notice every time I click on these cells here, it generates new random numbers, and that percent is always floating right around 90%. And I could also kind of change alpha to be 0.1 or 0.01, sorry. And then I'll kind of notice it's floating right around 99%. A little bit lower, sometimes right on, right? Just kind of depends on the random numbers that were generated. So I don't know, I always thought this is kind of a nice kind of example to really prove to ourselves using data that our confidence intervals really will include that true population mean, whatever percent of the time that kind of matches up with our specific alpha, our specified alpha. Okay. Any questions over anything else before I kind of let you guys get out of here? This is definitely something that more than I expect you guys to do, but I'll post it once I get back to my office. So I'm going to rebuild some of this because I didn't delete this. I only made the one slide blank. Although, is there anything interesting I could do here? We'll use this third worksheet. All right, so unknown population SD. Okay. So I've kind of actually on this data set, so I'm going to just delete these t-values in my upper and lower bound. I'm going to delete these guys right here. Go over. I've kind of got like two data sets here in one. Notice there's like a column that separates them. So here's a bunch of counties in 2012. Here's a bunch of counties in 2016. Okay. Now I've got drug deaths per 10,000 people here in each of those years. So what I'm going to do is simply take the average of that like death rate, right? Drug death rate. Hopefully we're pretty comfortable doing this in Excel at this point, right? To find our sample mean. And maybe to kind of be real clear here when I post this, and right, this represents my sample mean. And down here, I'm going to calculate my sample variance. Well, we've done this before, right? I'm just going to copy these, paste them down here so we kind of recognize these are all samples, right? We've done that sample variance before. That's just var.s, right? And we're just selecting the entire variable. So I'm not going to go through that again. We've gotten quite a bit of practice, I think, at that. So down here, what I need to do is find the t-value that gives me the desired alpha over 2 in the tail at whatever my degrees of freedom are. We just saw that how we can do that using the physical version of that table. But that table was somewhat incomplete, right? In fact, I'll actually add different alpha in here just to show you, like, we couldn't really do this one in the table. So let's say I wanted to do something like an alpha of 0.03. Well, if I go to that table, right, I don't have, that's not one of my 6 values here, right? If I really wanted to look at every single possible area in that tail, this table would be so wide, it wouldn't be very practical, right? But Excel, right, it doesn't necessarily have to kind of be restricted to a table, because remember, these values in the table are really coming from integrating the density function. We said that's not fun to do, and so people have already done it for us and created these tables, but in Excel, it'll actually do the integration behind the scenes for us. Okay? So when we were looking at an example on Monday where we knew the population standard deviation, we used that norm.s.inv function to find that z value that gave us alpha over 2 in each tail. So very similarly, we're doing the exact same process. It's just that we're, instead of using the standard normal, using a student t-distribution. So instead of norm.s.inv, all we do is use the t.inv function. So if you had set these confidence intervals up before, based off of what we did on Monday, everything would be correct except for you shouldn't have been using norm.s.inv, you should have been using t.inv. Because we only had a sample variance there for that final kind of problem 3. Okay. So the first thing I have to tell it is the area that I want in each tail, right, which is, or on each side of my confidence interval, which is alpha over 2. So I had up here earlier, but just as kind of a visual reminder, right? What we're really doing there is looking for these t values that give me alpha over 2 in each tail. Okay. Now, the problem is going to be if I treat this like the normal distribution. Oh, I forgot. This function actually needs 2 things, right? So I have to put a comma. The second thing I need to tell it is, well, which student t-distribution am I using, right? What's the degrees of freedom? Well, that's simply just going to be my sample size, which I have up here, -1. Okay. So now that I have this, it should give me that t value that gives me alpha over 2 in the tail. The only problem is, just like that norm.s.inv, it's always looking at that left side of the distribution. Right? So unlike the physical table, the function works, right? It's just integrating, kind of giving you the cumulative, right? It's looking at that left tail, everything below a certain value. Well, this is the value that we want, right? But that's the one we need for the lower bound. We need the same value at positive for the upper bound. When we actually type in these equations, those signs are already built in. So we said we just need the absolute value here. So we could use that absolute value function, close my parentheses. Now, if I try to copy this down so that I can get the t value that I need for these 4 different levels of confidence pretty quickly, what's going to be a problem? Yeah, this sample size cell reference is going to start moving down as well. I want my alpha value to change, but I don't want that sample size to ever change. So I'm going to put, oops, it's my F4 button. Not, oh, that would help, wouldn't it? I accidentally deleted that. There we go. Oh, one should be able to see this. So all I did there was F4 or Command T on a Mac to freeze that cell reference. Now when I copy this down, I'm getting all these t values pretty quickly. Okay. Any questions on that? You want to see one of those cells again? Or... So now it's really just kind of like what we did on Monday. Now I'll show you here how you do it all in one cell. I think on Monday, I broke it down so that I calculated that standard deviation of our sample mean or a sample portion in a different cell. Here, I'm just going to do it all on one line. So kind of like I have the equation written over there on the board or right here, right? We're not going to kind of calculate the intermediate or use the intermediate step, but it's, you could do that here as well and it'd be fine. So I'm going to take my sample mean. I'm going to subtract that t value or the number of standard deviations the way I want to go below that sample mean to build my confidence interval, and then multiply it by whatever the standard deviation of my sample means is, which is just the square root of my sample variance divided by my sample size. Okay. Similar to the examples that we did on Monday, the only thing that I want to change when I'm calculating the lower bound for different levels of confidence, only thing I want to change is that number of standard deviations away I'm going, or that t-value. So everything else, I'm going to freeze those cell references. Okay. Hit enter. Well, actually, instead of hitting enter here, I know that when I want to calculate the upper bound, it's going to be this exact same equation. So I'm going to copy that, hit enter to get out of the cell. So I'll paste this over here, and the upper bound is going to be the exact same thing. It's just that I add my margin of error. Okay. I hit enter. Now, when I copy these down, I've got 4 different confidence intervals pretty quickly. Okay. And notice I can even do weird values like alpha of 0.03, which I couldn't have used that physical table to do. Okay. Any questions over anything there? Went through a little quicker than, but yeah, like I said, once we get to that point, it's very similar to what we did on Monday. Oh, I thought there was something I wanted to point out here. Oh, so there are, let's see if I can even remember what they are. So there's these confidence.norm and confidence.t functions. I would, I don't teach them to you for a reason. I think they're a little bit more tricky than if you just kind of construct this on your own. Also, we're going to start doing some confidence intervals after this exam with 2 populations, and these don't quite treat them correctly all the time. So I don't show you how to use these, and they're actually going to just find what your margin of error is. They're not actually going to give you your lower and upper bound. So I would even say the name of them is actually, they should change the name of these functions. But if you Google how to do this, you might find this confidence.norm or confidence.t. I don't want you to do it that way. I mean, if you do it and you use it correctly, I'll give you full credit. I've just of the people that don't listen to me in class and then Google it and find this and use it, I would say maybe 5% of them do it correctly. So I would not suggest that strategy. I've got this, template up there for you. It's a really good, template for how you should approach that Excel homework. And also, like I said, those functions later on for future topics will start to not work for us. So I want to, make sure we know kind of how to set it up this way. Okay. All right. So I can do the exact same thing for 2016. At this point, I don't really need to type this in again. It should be the exact same student t values here, because I have the exact same sample size. Actually, yeah, because I have the exact same sample size. So I'll type in my lower bound equation. I'll take the sample mean, subtract that t value, multiply that by the square root of my sample variance over my sample size, right? It's the exact same thing I did for 2012. I'll then freeze the cell references for everything except for that t value. I'm then going to copy, hit enter, paste, and change that to add the margin of error as opposed to subtract it. So I've got 1 confidence interval. Now I've got 2 confidence intervals. Okay. So the reason why I kind of had these 2 years, I originally thought we might find something interesting about drug deaths. I always hear people don't like Indiana all the time. People say, act like it was huge. I mean,